Hello everyone, let's work more problems in E2 or E1 elimination reactions, and this is part of a continuation in the elimination chapter for problem solving. This would help you understand most of the mechanism in elimination reaction, the reagents, as well as isomers that could be formed during elimination reactions. Okay, let's see. Some of these problems are already on the board. I'm going to solve with some explanation to each one of them. As you see, the question here is draw all isomers and label as E1 or E2. This is just to say that you want to, based on the reaction conditions, you can identify as E1 or E2, as well as you give all possible isomers of the elimination reaction. Mainly, it is saying that constitutional isomers, not stereoisomers. Stereoisomers is a geometric isomer cis-trans, but here we just want to make sure that we eliminate from the right carbon and then give the position of the proper double bond. So on question 1, the condition, looking at this is methoxide base. Methoxides are strong bases. This is derived from sodium methoxide. So if you were to write the full reagent, it is like, it could be sodium or potassium methoxide. So it is a strong base. It is derived from sodium methoxide. So we call it methoxide base. So methoxide, ethoxide, all alkoxides in general. So in general, all alkoxides, which are represented by RO minus, are strong bases. Hence, if it is strong base, usually this should give you an E2 mechanism. So the reaction is an E2 reaction. And the products are, this is the alpha carbon, this is one beta carbon, and here is another beta carbon. So you would get two isomeric compounds as a product. So elimination from this beta hydrogens, eliminating one of these hydrogens would give you this isomer, right? And eliminating from this beta carbon would give you the following product. That is to say, you have this. So one terminal olefin that is less stable, but here one disubstituted alkene. So you get isomeric mixture of the both products. This is a disubstituted. This is a monosubstituted alkene. So moving on the second one, here it shows you not methoxide with full charge, but here the alcohol of it, methanol. So this is methoxide because it has a negative charge, alkoxide, but here this is an alcohol functional group. So when it is an alcohol functional group, it is very weak base, hence it goes usually through a carbocation mechanism. Hence, it would give you an E1 mechanism. So if we say E1, it goes through a carbocation, which is this carbocation, right? This is a intermediate species. Now we can lose from this beta carbon or from this beta carbon, giving you the same product here. So it would give the same this and also this product. So it would give the same product, but the mechanism is different because the reagent is an alcohol. And in this one, you see potassium tertiary butoxide, for example, can be the source of this. This is an alkoxide, a strong, bulky base. Hence, this would give you only, this is the alpha carbon, this is the beta hydrogens or beta carbon. So this has only one kind of product. This is the only product because that's the only position you could lose hydrogens from. Okay, in this D, you see here a tertiary halide, alkyl halide. So let me also characterize. This is a secondary that could go E1 or E2, but based on the reagent, it is an E2. This is a secondary as well, the same. This is a primary alkyl halide. Mostly this has to go by E2 mechanism. It cannot create a carbocation. Here you have a tertiary. Usually tertiary ones, they are easy to form carbocations, so therefore they always goes by E1 mechanism. And also because the carbocation that's formed is very stable, this is the carbocation that would be formed when chlorine leaves, and you have CH3 here. So this is the intermediate carbocation. Now, for this, the elimination can happen from this beta carbon or from this beta carbon. That is alpha carbon. So the product could give me, obviously this is an E2 one for the top one. This D is E1. That's why you have a carbocation, E1. But the products looks like two products can be formed, CH2, CH2, CH3, and double bond losing from here would be here, and you have this CH3, plus losing from this beta carbon would give us also another product which looks like this, CH3, CH2, CH2, CH3. So two isomers of different compounds. So those are the type of products you could get. If you just look at here, this is a tetra-substituted alkene. Here you see it is a tri-substituted alkene. 1, 2, 3. This is a tri-substituted one. This is a tetra-substituted one, tetra alkene. Mechanism-wise, it is an E1. Let's come here. Both are hydroxide, and the position of the chloride, the chlorine, are a little different, so they are isomeric already, so they should give different products. So this is the alpha carbon. Hydroxide is a strong base, hence it would be an E2 mechanism. The only product you would get would be, because whether you lose from this beta or this beta, the products are the same. Because if you flip it, it is the same molecule. So you will get only one product. It could be from here or from there. It doesn't matter. If I lose it, if you just turn it this, it will be the same product. So it is only one isomer you could get. But for this one, since the position of the chloride relative to this substituent is different, if you go that way and this way, then you could get different isomers. Still, it is an E2. Let's say this is the alpha carbon, this is the beta carbon. So this is beta carbon. So the two beta carbons are not equivalent. Here, the two beta carbons are equivalent, so you would get the same product. But here they are not equivalent because this beta carbon next to it is another carbon which has a different substituent. But here, this beta carbon next to it is a carbon which doesn't have a substituent. So if I lose first from this beta carbon, the product I would get would be, looks like this, because this is where I lose it. And the other one, if I lose beta hydrogen from this one, the product looks like this. So the distance, if you just look at this double bond, the distance from here to here is 1 carbon, but from this double bond to this, another carbon, from this double bond to this, so they are different. So these are isomers. So mechanism-wise, it's an E2. So basically what we have just solved is a problem of knowing the reaction condition, whether it gives an E1 or E2, and then identifying all the possible beta carbons which contain hydrogen and giving you different kind of isomers. So we'll continue more on elimination reactions. Let's continue with these two problems here. The problem asks us to rank the order of reactivity of this pair, this 3 and this 3. So we want to arrange with increasing order or decreasing. Let's say we would arrange this with increasing order of an E2 reactivity. This can be arranged as well of E1 activity as well. But for now, let me just first rank it for its E2 reactivity. Which one reacts the fastest in terms of E2 mechanism? As you know, E1 mechanism requires that they have to go through a carbocation. So for E2, you don't need a carbocation formation. So the reverse would be true. So E2 doesn't need a carbocation that should be formed. So for E2 reaction, if you just see a single mechanism, a single step mechanism, you would say this would be the primary alkyl halide, this is a tertiary alkyl halide, this is a secondary alkyl halide. So the least bulkier or least crowded would give you an E2 reaction faster. So the least crowded, or as the base is coming to abstract that proton, would be the primary alkyl halide. But in the second would be the secondary, then a tertiary. So if I were to arrange in order of increasing order of reactivity, if I label this as a compound, no, let's say this is, let's say, yeah, let me call it A, this is B, this is C. So which one would react faster in terms of an E2 mechanism? It is always true that the less hindered alkyl halide, which is, for example, a primary, which is at the halide is at the tip, but here it is 1 carbon in, it could be anywhere. So the reactivity increases from B is less than, B is much less than of the 3 of them. The least reactive one would be B in E2 mechanism, and the next one would be A, and the most reactive would be C. So this is order of increasing E2 reactivity. So it is in E2 reactivity, this is the order. So in E2 reactivity, C is the most reactive, the fastest, because it is a primary alkyl halide in E2 mechanism. So if we're asked to reverse this and study what would be the rate of the reaction if in E1 mechanism, that could be also asked. In E1 mechanism, the reverse is true. In the E1 mechanism, this is the fastest, because in E1 mechanism, you have to form a carbocation. A carbocation is easier to form from secondary, from the secondary than primary. Primary almost doesn't make a carbocation. So in E1 reactivity, now the fastest would be B, the least would be C. So C is much less than both of them. C is much less than A and much less than B. So here B is the most reactive in E1 mechanism. E1 reactivity, the order is this. So B is the most reactive. In E2 reactivity, C is the most reactivity. So the conclusion would be primary alkyl halides are easy to undergo E2 reaction, and tertiary alkyl halides are easy to react in E1 mechanism. So that is the conclusion. So after solving this should be much easier. So for E2 reactivity, if we just look at this is a secondary alkyl halide. This is a tertiary alkyl halide, and here is a tertiary alkyl halide. Now, there is one more thing you have to know in terms of reactivity. So, these are both equal, they are both tertiary. How do you differentiate in terms of their reactivity for forming an E2 mechanism? So for E1 mechanism, E2 mechanism, relative to these two, the fastest would be this. So if I say this is B, this is A, this is C, now the fastest would be B. So the least reactive would be the A, that would be the tertiary carbocation. It can form tertiary carbocation. So which one could form a carbocation is most reactive in E1 reaction. So the order would be A is much greater than B, greater than C, which is for E2 reaction. For E2 mechanism, in E2, the easiest would be the one which is C, is the fastest, and next would be A, the least would be B. So for E1, the least would be B, is less than A, but less than also C. So for E1 mechanism, the one which forms the carbocation much easier is this. So the most reactive is C in E1 mechanism, because bromine is a good leaving group than chlorine. Fluorine, chlorine, bromine, iodine. So iodine, if iodine was there, that would be the fastest. So here, bromine is a good leaving group. Bromine could leave faster than chloride. So in forming the carbocation, the tertiary carbocation, C is much preferable than A, but B is just secondary, so secondary carbocations are not that easy to form. How about for E2? In E2, the less hindered one is the fastest reactive, so it would be B would be the fastest. Okay, so B would be here, that's the fastest. And the next less would be, it would be between chlorine and bromine. Bromine is larger, so I would say bromine would be C here, less than, and it would be the least one would be C, which is bromine, and A would be the next one. So it would be like this. C is less than A is less than B. So the most reactive in this case would be B for an E2 reaction. And the fastest reactive in E1 mechanism would be C. So here there are two concepts we want to know. One, how good is a leaving group to form a carbocation? That's important concept. Second, whether the alkyl halide is primary, secondary, tertiary. For a carbocation to form, a tertiary carbocation can be formed from tertiary alkyl halide. So this is the fastest in the E1, and in E2 that is the slowest to react. So that's how you see it. So it's the reverse between E2 and E1 based on the mechanism of the reaction. So we'll continue. Okay, this continues almost the same kind of elimination reaction, but asking you rate of reaction, which one is faster. So we have in each of these three questions, we have a pair of reactants in different conditions and asking us which one would be faster. So the first thing I would be doing would be just to label what kind of reaction condition or what is possible in this as a mechanism. So in these two pairs, you have a chloride, which is alkyl halide. One is a tertiary and one is a secondary. Here you have a strong base. So what I would assume, the reaction is set up for an E1 reaction because it's a strong base which always favors E2. So E2 favors a strong base. So based on the reaction condition, I would say that in E2 reaction, this has to go faster because it is a secondary. But if it was an E1 condition, which is a very weak base, we would be saying a reverse. So here I am assuming an E2 reaction based on what I'm given here. So based on the hydroxide base, I would assume an E2 reaction. For E2 reaction, between the secondary and tertiary, if you compare them, between secondary and tertiary, secondary should react much faster. That's what we just discussed in the previous questions. So I would say this is faster, and the product looks like to be, it could be either this, CH3, plus this would be 1. Oh no, it could be this and CH3 here. So this is faster between these two because I'm considering this to be an E2 reaction based on a strong base. So this is a strong base. That's the rationale. So between these two, you get the product for this. I want to give the product for that also. The product should look like we have this. And also if you lose from this one, you should get something like that. So those are the products that you'd get, but overall the reaction is faster for the lower one. Here you have a tertiary butyl chloride. This is tertiary and this is tertiary. Both are the same. But the only difference here, if you can just look at closely, be careful, this favors an E1 mechanism. Okay? This is E1 because the base is weaker in a polar protic solvent. This is polar protic solvent. Polar protic solvent. So here they didn't mention the solvent, so I'm assuming it as just a strong base, and hence I'm considering E2 reaction. But for this one, the top one is a polar protic solvent, and it is an E1 mechanism. Here I have a polar aprotic solvent, DMSO, polar aprotic. So no proton on it, protic solvent. Polar aprotic solvent mechanism is E2, is favored. But if you just see the reaction condition we were given, it is one is for E1, one is for E2 type. But you should also examine what the substrates are given. So, as I already mentioned, a tertiary alkyl halide, all tertiary alkyl halides, they go through carbocation. So for carbocation, this is the one which goes through E1 that is favorable. So this is the faster reaction. The top one is faster because the reason is this is tertiary. The reaction condition is for E1. Tertiary always undergo through E1 mechanism. Therefore, that would be faster. So this will not be, the rate would not be comparable. That requires an E2 mechanism because it is polar aprotic solvent. So the top one is faster. Here the lower one is faster. What about here? Let's characterize first what we have. Both here, the base is a very weak base. Water is a very weak base. So since I have a very weak base, the reaction condition is, or the mechanism that is favored would be an E1 mechanism. So here, E1 mechanism, both, because we have a very weak base. So let's now then characterize this, the alkyl halide. But the alkyl halides are also different. Here I have a secondary alkyl halide. Here I have a tertiary alkyl halide. In E1 mechanism, a tertiary alkyl halide is favorable. That's because it forms a carbocation. Therefore, this one is the faster reaction. Faster reaction is this. And the product would be, because it goes through carbocation, the chlorine leaves. Since I have that, you could get a loss of the hydrogen from this beta carbon or from this beta carbon. This is intermediate carbocation. So the products look like one is from losing from here, or losing from that would be that. So these two isomers can be formed in E1 mechanism. I would say the reaction is faster for the lower one than the top one. So this is how you evaluate the reactivity or how fast the reaction goes. So the strategy is first to identify what is the condition. What is the mechanism that is possible under that condition? So by just looking at the base, the solvent that is given, you would identify the mechanism, whether it's an E1 or E2. So once you find out that, you go and evaluate what kind of alkyl halide I have. Do I have a tertiary alkyl halide, a primary alkyl halide, or secondary alkyl halide? In general, primary alkyl halides are easier to undergo E2 in general. Primaries are always good for an E2, and tertiary ones are good for E1. So the secondary are in between this. So it's, you'd examine that based on the reaction condition. But always primary alkyl halides are for E2, they are good for E2. Tertiary alkyl halides are good for E1. That's why I have here for E1, I have a tertiary, not a secondary between these two. Of course, when you evaluate between these two, this is a faster reaction. So that's how you evaluate. Evaluate the alkyl halide, evaluate the mechanism of the reaction based on what are the reagents that are given. Do I have a strong base? Do I have polar aprotic solvent? Do I have polar aprotic protic solvent, and etc. So that's how you would evaluate any problem. We have an interesting question. Compound A, which is an alkyl halide, is treated with sodium methoxide, strong alkoxide base, and here it is ethanol. So the difference between these two would give us, when you treat it with sodium ethoxide, it only gives major dominant product only B. But when you treat the same molecule with a weaker base, it gives you compound B, obviously, and C as a major product. So two products, but C is also a new major product different from this one. So explain why do you get this two products here, major being C, but here you get only one compound, B. So now this is very interesting, and you need to think closer to the problem. So in the top case, it is a strong base, which suggests that it goes through an E2 mechanism. That's the first thing I would write. In the case of treating A with ethanol, it is a very weak base, alcohols, that's polar protic solvent. It goes through an E1 mechanism. So in the transition state, in E2 case, both the base approaching the alkyl halide and also the alkyl halide are in the transition state. So sterics is very important. Sterics, meaning that overcrowding the environment is not a good thing for an E2. So when you come close and see here, this is the beta hydrogens here and the beta hydrogens from here. The product that's formed here is only from this beta hydrogen, not from this one. What it says is that when the base comes in, tries to pull, always it pulls from the less crowded, it picks the less crowded hydrogen. That means if you have these two hydrogens here, and this beta carbon, there is one hydrogen here inside here. It's behind this large group. So in E2, in the transition state, both are implicated. That means anything that is sterically crowding cannot be a feasible transition state. So the base comes in, pulls off this proton, or the base comes in, pulls off that hydrogen. So it didn't pull this hydrogen because this area is bulky. So this proton is sterically hindered. So since there is a sterics here, the base only comes in E2 reaction, since the halide and also the base are implicated in the transition state, they have to be together. So when it comes in here, it prefers not to come here, but to pick this proton. So you have only this product as a result of that. Right? It's very interesting, good question to think about. But in this reaction, in the lower case, when you have ethanol as a base and a solvent, the first initial thing that happened is only the halide would just lose itself, it would be dissociating and forms a carbocation. So the base doesn't have to come in a crowded area first. You have this, okay? you have this, you have this. So in the transition state, the chloride has already gone, so this is not sterically demanding in the transition state. So slowly, in the fast state, it can abstract this proton or that proton. So it has a choice. So the rate determining step, which is the first initial removal of the halide, would be less energy demanding. But in this case, in the top case, first you have to have the base coming in, the halide is still there. So sterically, it is very important to pick up the less crowded hydrogens for an E2. But for this one, since the halide has already been gone, it has a chance for a base, which is the ethanol, CH3CH2OH, to come in and pull off that proton. Or it can also come from this side, OH, CH2, CH3, or pick up this proton. So possibilities are there for this to come here and for this to come here, because this is now not sterically crowded. Here you have a chloride, and the E2 has to come in, has to take this. So it cannot come and take at the same time while the chloride still is there. So the difference is now E2 versus E1. The E1 mechanism provides us a very not sterically hindered species that can abstract from both sides. So this is due to abstraction of this, you get the top one, and from this abstraction you get this one. Now the question is, okay, I'm forming B and C in the lower case, but why C is the major one? Obviously we know that now, and you see the nature of the alkene. Which one is more stable alkene? Here the alkene, as you see here, is a di-substituted alkene, because you have an R group here, an R group here. So this is a di-substituted alkene, di-substituted. But here, as you see, you have one hydrogen only there. You have an alkyl group here, an alkyl group, an alkyl group. So this is tri-substituted alkene. So according to the Zaitsev rule, a tri-substituted alkene is much more stable than a di-substituted alkene. That's why you get this as a major product. So overall, what we have done is now identified why this is the only product that's formed, because sterics is important in E2 reaction, because the transition state has to hold the alkyl halide at the same time the base in the transition state. But since chlorine is still there during the transition state formation, that always goes, the base always goes for sterically less hindered. These are sterically less hindered. That's why the base tries to abstract from here, not from there. So the approach for the base during E2 reaction is to this hydrogens, to one of them, not to this hydrogen. But here, the base abstraction comes after the alkyl, the halide has left, so this area is not sterically hindered. Therefore, the base has a chance to come to this proton, to that proton as well. Therefore, it gives you two products. The C is a major because it is a tri-substituted alkene. Okay, we're going to continue more on. Okay, we have an interesting question which encompasses different concepts. The question is, what is the major E2 reaction product for these two, reaction A and reaction B? So here you see these two compounds are presented as a Newman projection. This is very back into the chapters, mostly in the introductory part of our organic chemistry course. So for E2 reaction, we have also concluded that anti-periplanar arrangement between the hydrogen that's to be abstracted and the halide that would leave dehydrohalogenated would be anti-periplanar. What's anti-periplanar? The concept of anti-periplanar means that the hydrogen and also the halide should be in the same plane, and they have to be 180 degrees. So here this is already the hydrogen that's potentially on this beta carbon. The alpha carbon is into the plane of the board, which is containing this. This hydrogen and that bromine are actually anti-periplanar already. To make sure that you really could see it very clearly, I could redraw it by rotating this 120 degrees, and it would be the same molecule. The way I would redraw this by removing this 120 degrees, that means if I bring this here and bromine here, they will be anti-periplanar. So the way I would rotate them is a clockwise rotation by 120 degrees would give me this hydrogen to be here, and then this metal group to be right there, and this ethyl group to be right here. So this is the configuration now we have. So bromine is right here. Still I didn't touch it yet. C6H5, and this is CH3. So to make sure that I have the hydrogen and the bromine anti-periplanar, I would rotate the back three groups by 120 degrees. So that would give me, I will keep this the front as it still is, CH3, C2, CH2, CH3, rotating the back by 120 degrees, the back, only the back ones. Bromine would come here, right? So when bromine comes here, CH3 goes here. When C6H5, the phenyl group, would be here. Now we have everything set up. That means the hydrogen and bromine are at 180 degrees. That means anti, but they are also in the same plane. Like if you have a plane of board, or if you slice it like this, H and Br would fall on the same plane. Now you could do the dehydrohalogenation, meaning the elimination E2 reaction. So when this is abstracted by a base, this collapses back to the back bond to make a double bond, but C6 and CH3 would be on the same phase, and CH3 and ethyl would be on the same phase. That means the product would be CH3 would be here, C6H5 would be here. You could imagine this by just looking at that. And obviously these two would be on the same side. That means CH2 would be here, CH2, CH3, and the CH3 would be here. So that's the product. The major product of this elimination reaction looks like that. So this is very important. This is just, let's continue on the second one. So we will do the same thing what we have done in the top one. So now Br is still here. If I bring hydrogen here from the one which is at the back, they will be anti-periplanar, right? So the way I will do that would be keep the front the way it is, because bromine is here. The only thing is I want to bring hydrogen here. So the way I will do is, if I rotate counterclockwise, this is clockwise, this is counterclockwise rotation, meaning like this, not like that. So rotate this, the back one, keep the front as is. So if I keep the front as is, CH3, and hold the back and rotate it like this by 120 degrees, hydrogen would be here. So when I rotate hydrogen here, ethyl group would come here, CH2, CH3, and the CH3 group would be right here. Exactly this. Now I have the bromine, which is a halide, and the hydrogen, anti-periplanar, 180 degrees anti-periplanar arrangement. So when hydrogen comes in, a base comes, takes that proton away, it will put the double bond across this carbon and the other carbon inside the plane of the board. So CH2 and CH3 would be on the same side. That means CH3 would be here, CH2, CH3 would be here. That means CH3 would be here, and the C6H5 phenyl group would be here. So that's what we get. So now, these are the alkene products after E2 reaction. This is after E2 reaction. So the main important thing you want to know about this is that you have to arrange the hydrogen and the halide as anti-periplanar for the E2 reaction to happen. That would fix where things would fall. So this and this are the same side, C6H5 and CH3, and CH2, CH3 and CH3 are on the same side. As well here, CH3 and CH2, CH3 are on the same side, and C6H5, CH3 are on the same side. So in terms of what the stereochemistry or what the stereoisomers are, I believe the priority between these two is, this is high priority because it has two carbons. This has only one carbon. Priority is for this one. And for this one, between these two, the priority is this one, C6 versus CH3. So the two priorities are on opposite. So this is an E isomer, or trans, or E. And for this one, between this and this, the priority would fall for this one. And between this to this, priority is this. So the two high priority are on opposite sides. This is also an E trans isomer, stereoisomer. So this is whenever you are given a Newman projection and dehydrohalogenation, you have to do a certain manipulation so that you could arrive at the right stereoisomer. So this is the concept of anti-periplanar. What it means is the halide and the hydrogen that would be abstracted. This is, for example, in this case, this is the beta carbon. The alpha carbon is inside the plane of the board. So inside, so that's holding the halide. In this case, this is the alpha, the front one, and the beta is holding this hydrogen back. So it is at the back. So the beta is at the back carbon. So this is how you would solve things when you are given in a Newman projection for an E2 elimination reaction.